Hey everyone, welcome back. Today we are going to be looking at our Unit 10 Day 3 lesson, which is going to be on the volume of prisms. So yesterday Miss Flowers walked you through how to find the lateral area and surface area, which were different measurements that went around the outside of a three-dimensional shape, in yesterday's case the prism. However, today we're going to be talking about what volume is. So we want to be able to, one, define what volume is, and two, we want to be able to use the volume formula in order to solve problems. So first thing we're going to do in this warm-up, and this is a little different than how we would handle this when we would meet in class. If we were meeting normally, I would have you watch this video on your own, make your guesses, and things along that line. So if we just decided to basically watch the video, you can pause it, take a look, but what you're going to end up finding is just a very short clip of a jar getting filled with the Whoppers candy, and you're asked to make a guess as to what that value is. If you want to go ahead and do that, you can. The video does not show exactly how many there are, but what I ask that you write in that warm-up box are some pieces of information that would help. Okay, and that could be a variety of things. So I'm not going to try to direct your attention one way or another with writing some things down on my own. I'm going to let you kind of choose what you feel would be helpful for you to know what that answer is, obviously, other than just saying, oh, well, it would be helpful if I knew how many Whoppers were in there, right? What other information could I tell you that would help you arrive at a close, if not exact, answer? Okay, but that's for you to do on your own. We're going to jump right into our definition of what volume is. So up until this point, with our three-dimensional shapes, we've talked about lateral area and surface area, and that was explained to be the area of all of the sides. In other words, we were finding how big the outside or the exterior of the shape was. But when we talk about volume, what we want to know is the amount of space inside of a three-dimensional figure. How much space is on the inside? How much of a substance can a three-dimensional shape hold? Now, one big difference between volume versus lateral area and surface area is that volume is measured in units cubed. So, for example, we might say something like inches cubed or cubic inches, feet cubed. Notice the exponent is a 3. This happens anytime we are working with volume. Volume will always be units cubed. Now, the formula in order to find the volume of any prism is very, very simple. We can see that the volume of a prism is equal to B times H. Yesterday we learned that B represented the area of the base, and H is obviously the height. How far is it from one base to the other? So I'm going to put that as a little extra note. Remember that height of a prism is distance from base to base. Now, you can also see that there is a very special case in the event that we have a rectangular prism. This only works for rectangular prisms, so I'm going to kind of make that stand out again. There's all types of prisms. We have pentagonal prisms, hexagonal prisms, trapezoidal prisms, you name it. This special case formula, LWH, only works for rectangular prisms. Okay? If it's not a rectangular prism, then we are using this B times H. Now, with LWH, what do these stand for? It's probably something that you've already learned previously in middle school. L is the length of the prism. W is the width of the prism, so how far front to back, and H is the height of the prism. So if I were to just draw a very generic prism, this side-to-side measurement would be L, the length. How far is it side to side? This front-to-back measurement would be the width, and that vertical component would be the height. So if we have a rectangular prism, all we would have to do is multiply those three dimensions together, L times W times H, and that would give us the volume. Okay. So as we look at our first example here, and for all of these examples, it asks us to find the volume of each prism, rounding to the nearest hundredth. So in the event that we do get a decimal, we want two numbers after the decimal place. So in this case, I look and I see that this would be a rectangular prism, right? We don't see those additional sides, but if I were to draw them in, we see that this bottom piece right here, that bottom base, is in fact a rectangle. So in this case here, we can simply use our volume is length times width times height. We see that the length is 8, the width is 3, the height, let's write that as a 3, and the height is 2. Okay, obviously not drawn to scale, but all we'd have to do is do that multiplication. So 8 times 3 is 24, times 2, this is going to be 48. Our unit is meters, and since this is volume, we are going to cube that unit. 48 meters squared. I'm sorry, meters cubed. Okay. When we take a look at our second one, again, we see that this is going to be another rectangular prism where this bottom base is a 30 by 7 rectangle. So again, volume is going to be L times W times H, where we see the length is 30 across, the width is 7 front to back, and the height is 6 up and down. 30 times 7 is 210, times 6 is going to be 1,260 inches cubed. Okay. So those first two are very, very straightforward. And again, I'm assuming this is a formula and type of example you've seen before in previous math courses. Okay, but where it starts to differentiate a little bit is when we start to get things that are not triangular bases. So we see, not rectangular bases. So in this case here, we can see we have a triangular base. We have this triangle up on top. We have its corresponding or matching triangle base down on bottom. And then we can see the distance from one base to the next is 7. So in this case, we cannot use length times width times height. It's not a rectangular prism. So instead, we have to use this generic formula, volume equals capital B times H, which means area of the base times the height. So what I'm going to do up here is basically just do my calculations as needed for each of those two variables, substitute those in when we have them, and then find our final answer. So in this case, the height is actually very straightforward. The height is 7. From one base to the next, or the bottom triangle to the top one, that's a difference of 7. Capital B, remember, is the area of the base. Miss Flowers did a really good job emphasizing that yesterday. It's the area of the base. So a very common error that'll get made is students will say 4 is B. And remember, that's the base of that triangle, but it's not the area of the base of the prism. So we want to recognize that this base is a right triangle whose two legs are 3 and 4. So we use the area of a triangle formula, 1/2 times base times height. In this height we're using in this formula, this 3, that's the height of the triangle, not the height of the overall prism. So we want to be very careful when we say H, what height are we referring to? The height of the prism or the height of the triangle that's the base of the prism? Okay, so in this case, 1/2 times 4 times 3, well, 4 times 3 is 12, half of that is 6. So now I've got my two variables solved for. The area of the base is 6, the height is 7, so if I multiply those two together, 6 times 7, 42, and my unit, feet cubed. Okay. Now in this case, we have a cube. Now a cube is a special type of rectangular prism. So the only difference is a rectangular prism has the freedom to where not all the dimensions need to be the same. In a cube, it still follows that same pattern. It's still got that same look, except all edges are the exact same length, in this case, 9. So I am allowed to use my volume formula, length times width times height. The length is 9. The width is 9. The height is 9. We can also think of this as 9 cubed, which kind of helps explain how this shape got its name. It's the same dimension cubed, length times width times height. So if we were to do 9 cubed, or 9 times 9 times 9, that comes out to be 729. In this case, they did not give us units, so that is just going to simply be units cubed. Okay, so a cube does fall into that category, or that special case of a rectangular prism. Okay, 2 more examples here. Equilateral triangular prism, so it's telling us that the base is an equilateral triangle. Okay, we've spent quite a bit of time last unit talking about that. So, because it is a equilateral triangular prism, not a rectangular prism, we go back to our general capital B times H. Capital B, H. Let's start with H. It's the easiest one, and it even tells us in this case H is 6 centimeters. It's the distance from one base to the next. The height is 6. Capital B is the area of the base. Well, it tells us again that the base is an equilateral triangle. So we want to refer back to that previous formula that we learned last unit. Area of an equilateral triangle is s squared root 3 all over 4. In this case, we can see the side of the equilateral triangle is 3 each. So the area of the base is going to be 3 squared root 3 all over 4. Okay, quick calculation here. 3 squared root 3 divided by 4 comes out to be approximately 3.9. And that's the area of the base. So to find the volume, we're going to take that area, 3.9, and we're going to multiply it by the height, 6, and that's going to give us a grand total of 23.4 centimeters cubed. Okay, find the area of the base, and this is why success in last unit is so beneficial now, because we're taking that information, how do we find the area of any given shape, and applying it now to a three-dimensional figure, which makes more sense because we live in a three-dimensional world. Okay. Lastly, trapezoidal prism tells us that the base is a trapezoid. So, one more time, volume is B times H. Capital B is the area of the base. H is the height. Now, common errors that might get made. Students may say 20 is the height. 20 is the height of the prism. It's the height of the trapezoid. It is not the height of the prism. Height is not always up and down. Height could be side to side. Height could be front to back. It all depends on the layout of the shape. When it comes to any prism, the bases are going to be across from each other, and since this is a trapezoidal prism, that means these two trapezoids at the front and the back are the two bases. So if I want to know the height, I want to know the distance between them. This trapezoid is laying down on its side. If it were to be upright so that the two trapezoids were on top and bottom, it would have a height of 80 centimeters. So that's going to be our height. Now the area of the base, we want to use our trapezoid formula, which was 1/2 times the height of the trapezoid. In this case, now we use that 20. And then parentheses, inside the parentheses was base 1 plus base 2. So the two bases were 45 and 60. And we can type that into our calculator. So if I were to quickly do that, 1/2 times 20 times what ultimately becomes 105, it becomes 1,050. So now we have the area of the base, we have the height, we multiply those together. 1,050 times 80, let's get a quick look here. That comes out to be 8,400, and my unit is centimeters, so centimeters cubed. Okay. So in all of these cases, we were able to calculate the formula by either doing length times width times height if it was a rectangular prism, or if the base was anything other than a rectangle, or in the cube's case a square, we did B times H, area of the base, times the height. Okay? So now some word problems where we can just apply this. If you want to basically cut it off here, you can. If you want to look through some application style problems, you may. It's up to you. Okay? But if we continue on here, we can see that Drew and Kelvin are digging a tunnel through a mountain. The space inside the tunnel is going to be shaped like a rectangular prism. The dimensions of the tunnel will be 20 feet high, 50 feet wide, and the length of the tunnel will be 900 feet. How much land will need to be removed from the mountain in order to create that tunnel going through? Well, given that it's a rectangular prism and that we were given all three dimensions, this is pretty straightforward. Okay, it tells us that the length of the tunnel is 900 feet. So there's my length. My width is 50. And my height is 20. So a quick calculation, 900 times 50 times 20. And that comes out to be, big number, 900,000. 900,000 feet cubed. Okay, so how much is that? Imagine if you had a cube in front of you that was 1 foot in each direction. Okay, so you could grab a ruler and take a look, or think about like a tile on the floor that basically comes up a foot off the ground. That would be 1 cubic foot. You would have to remove 900,000 of those. So quite a decent chunk of land there. Okay. Next one. Monty's rectangular swimming pool has a volume of 16,320 cubic feet. A depth, so we know the volume. It's got a depth of 8 feet and it's got a length of 85 feet. What's the width of the pool? So again, given that it's rectangular, we know that the volume is length times width times height. And this is a perfect example of our working backwards problems where we already know the volume and we're trying to figure out one of the dimensions that produce that volume. So the volume is 16,320. So we'll place V with that. The length we were given to be 85. The width we don't know. That's what we're trying to find. And the depth, or the height, of the prism is 8. So, just as we did before, we are going to combine our like terms. The 16,320 stands by itself. I'm going to multiply 85 times 8, and I'm going to get 680 times W. Last step, we want to divide both sides by 680, and that result is going to tell us the width. So 16,320 divided by 680 comes out to be 24. Now remember, 24 is the width. It's a one-dimensional unit, front to back. There's no up or down. There's no side to side. So it's 24 feet, not feet squared, not feet cubed. The width of the pool is 24 feet. Okay? Now, the last one is a pretty cool example, and it's more real-life applicable than some of these other ones are. The human body is obviously different shapes for different people. It's not a perfect cylinder. It's not even a combination of perfect shapes. So in order to find its volume, it's actually pretty challenging to do, provided you don't have the right equipment. But a pretty simple way that's been found and done is to do something like this. You find a tank of water that's in the shape of a rectangular prism, a cylinder, something that is very easy to measure. So in this case, a tank of water is 10 feet long, 6 feet wide, and it's filled so that the water is 4 feet deep. So there are 3 dimensions: our length, our width, and our height. Now, what we're able to do, well, let's keep reading on first. A person then submerges himself into the tank. So the first question that I want you to think about is just real life. What would happen if you've got a tank full of water and then someone goes into the water? What would happen to the length, the width, and the height of the tank, okay, or the water in the tank? So what would happen to the length? Well, the length is restricted. By going into the tank, it's not going to expand and get wider. So the length is fixed. It's not going to change. Same thing with the width. The pool isn't going to get any wider by someone going into it. However, what's going to happen to the height of the water? Well, when a person goes in, that water needs to be displaced somewhere else, and the only direction that it can go is upward. So the height will rise. Okay? And then ultimately, that's helpful because what that allows us to do is now find out how much volume was added into the pool. So it says if the water is now at a height of 4.2 feet, what is the volume of the person? Okay, well, what we don't want to do is this. Well, the height is 4.2 and the original was 4, so 0.2 feet. Okay, we did not do anything with the volumes in that case. We just took the difference in heights. First thing we want to do is we want to find what's the volume of the original. So the volume before the person got in. Length was 10, width was 6, height was 4. So that's going to be 6 times 4 is 24, times 10 is 240 cubic feet. Now if we find what was the volume after the person went in, the length was still 10, the width was still 6, but now the height is 4.2. So that'll be 10 times 6 is 60, times 4.2 comes out to be 252 cubic feet. Okay, so then the last thing we would have to do is a quick subtraction. 252 minus 240 is 12. So that means the dimensions or the volume of the pool changed by 12 cubic feet once the person was added. Therefore, the person has a volume of 12 cubic feet. That's how much they take up. Okay? So, saw a lot of really good examples here, different types of bases. But again, every type of calculation is something that we've done many times before, whether it was last unit or even this unit. So, if you have any questions, as always, please feel free to contact your teacher through email or through Schoology, and we will be more than happy to assist you in any way that we can. There is an assignment available for you to get that practice. So if you have any questions with that, let us know. Thanks for watching. Have a great day.